Hello friends, let's start off with complex numbers, chapter 5. The introduction and exercise 5.1. So how do we do this exercise? We'll just see. So before that we'll go into what is the introduction of this. So here we have already seen what is a quadratic equation. We all know what's a quadratic equation. Quadratic equation, we write it as ax square plus bx plus c is equal to 0. So here in previous 10th class we have learned how to find out the roots of this. So what is the root? We find out x as equal to minus b plus or minus root of b square minus 4ac by 2a. Now root b square minus 4ac is called the discriminant. We have seen that here b square minus 4ac is greater than 0 means the roots are real and distinct. So here then if it is, that means b square minus 4ac is less than 0 means the roots are not real over here. So we did not find out any roots over here. We stopped the problem over here telling that the roots are not real. We cannot find out the roots. But over here now in this case, whenever we are going into complex numbers, suppose you are having x square minus 9 is equal to 0. So how do we go into complex numbers? We'll just see. You can just write this as x square is equal to 9 or x is equal to root of 9, which is equal to plus or minus 3. Now we also can write x square plus 9 is equal to 0. So here x square is equal to, what are we getting? Minus 9, or x is equal to root of minus 9. Whenever we are getting under root minus 9, we were telling that the roots are not real because there is a negative number inside the root. So now how do we find out this root? We'll just see in this complex numbers we'll be finding out the root of the value of this term where x is equal to root of minus 9. So how do we go into complex numbers? We'll just see. In complex numbers, what is a complex number? We'll see first of all. So we all know what are natural numbers. It is starting from 1 to 3 so on. Then we know what are whole numbers. It's including 0, 1, 2, 3 and so on. Then we had what are integers. In integers we had all negative values and positive values with including 0. Then we had what are rational numbers. Rational numbers which were denoted by this, that is, it is equal to set of all p by q where q is not equal to 0. Then we had what are irrational numbers which was denoted as q dash, which cannot be written in the form of p by q where q is not equal to 0. So not of the form p by q where q is not equal to 0. These were irrational numbers. Then we had what are real numbers. In real numbers it is the set of all the above numbers, the combination of all the above numbers. It had what are natural numbers, whole numbers, integers, rational numbers, irrational numbers. It's a combination of all real numbers. Now this complex number is nothing but it is a combination of real number and an imaginary number. So now where does this complex number come into scene? We'll just see. Now what is this imaginary number over here? imaginary number we denote it as iota. So now where do we get this imaginary number? We'll just see. Suppose we are having root of minus 4. So this can be written as root of minus 1 into 4, right? And this can be written as minus 1 into root 4, which is equal to, you can write this as minus 1 into 2. So now what is this value of minus 1? Just remember here, root of minus 1 is equal to nothing but I. This is called as iota, or if you're squaring on both sides, you're getting minus 1 is equal to I square. So this, or iota square, this is an imaginary number where I is an imaginary number. So now what is this example of a complex number? You can write it as a combination of a real number and an imaginary number, something like this, or you can also write it as 2 plus 5i. So now while going into all this type of, so always you have to remember one thing in this, that all imaginary numbers, whenever it is in combination of a real number, or if it is taken alone, wherever we are finding out negative roots, that is said to be this complex number come into picture when we are finding out the negative roots of under root. So here if you are taking an example, it's a combination of real number and an imaginary number. So now we'll just see how to solve this imaginary number. Taking this imaginary number, how do we find out the values? Where do we use this? Especially we'll just see. So now here, what is the addition of complex numbers? What is the multiplication? What is the subtraction? What is division? We'll see. So taking this example itself. So here, addition of complex numbers. So how do we do this complex number addition? We'll just see. Suppose if I take here z1 is equal to 3 plus 4i and z2 is equal to 2 plus 5i. I have taken the same examples here. There are so many examples which you can write down. Even you can write wherever you are getting into senior minus 9, minus 5, or under root, wherever you are getting minus inside the root, there the complex number exists. So examples you can write all those. Now here complex number z is equal to, your addition means you are adding here z1 plus z2. So this is equal to 3 plus 4i plus 2 plus 5i. So now here like terms we add all the real numbers and then we add all the complex numbers. So you are getting it as 5 plus 9i. This is equal to z, the addition of complex numbers. Next, what is subtraction of complex numbers? We'll see. Subtraction of complex numbers. So now here z is equal to z2 minus z1. If we take the same example we are going to take, so which is equal to 2 plus 5i minus of 3 plus 4i, which can be written as 2 plus 5i minus 3 minus 4i. So which is equal to minus 1 plus I. So this is the answer when we are doing subtraction of complex numbers. Next we will go into what is multiplication of complex numbers. So how do we do the multiplication of complex numbers? We'll see. So here now suppose z is equal to, the same example we'll take z1 into z2. So how do we write this? We write it as 3 plus 4i into 2 plus 5i. So same way how did we do in 10th class? We'll do in the same way. Multiply this 3 with both these numbers. Multiply 4i with both these numbers. So you'll get here 3 into 2 is 6. 6 plus 3 5s are 15i plus 2 into 4i is 8i square. You're getting here, I'm sorry, 8. Then plus 4 into 5 is 20i square. So which is equal to here 6 plus 15 plus 8 is 23i, plus here you are getting it as 20 into minus 1, because you know that I root of minus 1 is I and iota, and I square is equal to minus 1. So therefore here you are getting it as 6 plus 23i minus 20, which is equal to minus 14 plus 23i is the answer which we are getting for this problem. Next, what is division of complex numbers? We'll see. Division of complex numbers. So how we solve this division of complex numbers? Same way we'll take here. Z is equal to Z1 by Z2. So here we are having Z2, Z1 is equal to 3 plus 4i divided by 2 plus 5i. So now here whenever we are writing any complex number in this form, in the denominator you have seen in your previous classes in last year, whenever we are having root in the denominator, we rationalize that. We remove the root in the denominator. So in the same way we can do it. We can write this as Z is equal to 3 plus 4i divided by 2 plus 5i. Here also we will multiply by 2 minus 5i by 2 minus 5i. So here you will get it as equal to 3 plus 4i into 2 minus 5i. I am calling iota as I because it's comfortable for me to speak in that way or to call it out in that way. So here now a plus b into a minus b you can written as 2 square minus of 5i whole square. So again here in the numerator you have to multiply. You are getting 6 here plus 8i minus 15i. So you are getting it as minus 7i minus 20i square. It will give you minus 20i square divided by, here you are getting 4 minus of 25i square. So iota square is nothing but equal to minus 1 over here. So we'll substitute here 6 minus 7i plus 20 divided by 4 plus 25. So which is equal to 6 plus 20 is 26 minus 7i divided by 29. So now you can write this as 26 by 29 minus 7i by 29. It's a combination of both a real number and a imaginary number is complex number. So now we have seen all this. Now we are having some special cases wherein you suppose you are having given a problem I to the power of 5. How to solve this problem? You can write this as I to the power of whole square, or you can write I to the power of 4 into I. Now I to the power of 4 can be written as I square whole square into I, which is equal to I square is nothing but it's equal to minus 1. So you're getting a minus 1 whole square into I, which is equal to minus 1 whole square is equal to 1. So you're getting the answer as I. So in the same way, suppose you're having here I to the power of 23. How do we write this I to the power of 23? I to the power of 22 into I we can write. So this can be written as I square whole to the power of 11 into I. So now which is equal to minus 1 to the power of 11 into I. And whenever you're having the power as an odd number, you can write this as minus 1 into I, which is equal to minus I. This is the answer. So in this way we can do many powers. We have to split it and write it down in this way. Now we'll see what is additive inverse of complex number. So now what is the additive inverse of complex number? Suppose we take it as 2 plus 3i. So additive inverse of 2 plus 3i. Now suppose you're taking this as z. So additive identity number of this will be equal to it should be equal to 0, isn't it? So additive inverse of z is minus 2 minus 3i is minus z, that is minus z. So that is, you will get it as 2 plus 3i minus of 2 plus 3i. So you are taking the negative of that, which is equal to 2 plus 3i minus 2 minus 3i, which is equal to 0. So this is the additive identity. So and here this is the additive inverse. So additive inverse of z is minus the negative of the given number. Now what is the multiplicative So what's the multiplicative inverse of this, we'll see. So for additive inverse it is minus z, remember that. Then multiplicative inverse of complex number, so if z is equal to the same number, we can take 2 plus 3i. The multiplicative inverse is equal to 1 by z, which is equal to 1 by 2 plus 3i. So here whenever we are taking in this case, here you have, because in the denominator you shouldn't have a complex number, so we will write it as 2 minus 3i by 2 minus 3i, which is equal to 2 minus 3i by 2 square minus of 3i whole square, which is equal to 2 minus 3i by 4 minus of 9i square, which is equal to 2 minus 3i divided by 4 minus of, because I square is equal to minus 1, so you will get here plus 9. So which is equal to 2 minus 3i by 13. This is the answer. You can write it as 2 by 13 minus 3i by 13. So in this way we can do all the, this is the introduction of your complex numbers. Now we can go into what is exercise 5.1. So how can we do the first? Express each of the complex number given in the exercise 1 to 10, that is the problems 1 to 10, in the form a plus ib. So first problem which is given, solution for the first one here. How do we write this? It's equal to, here you are having 5i into minus 3 by 5i, which is equal to, you can write this as 5i into minus 3 by 5i. Here 5i and 5i will get cancelled, so the answer is equal to minus 3. How do we write this in this form, complex number form? So you know the general form of a complex number is a plus ib, a real number and an imaginary number. So now we got this answer here as z is equal to minus 3 plus, we don't have here an imaginary number, so we write it as I into 0. So the first one can be written in this form. So here you are having it as I to the power of 9 plus I to the power of 19. I to the power of 9 plus I to the power of 19 can be written as, you know this can be written as I to the power of 8 into I plus I to the power of 18 into I. So which is equal, because you know what is a to the power of 4 into a can be written as a to the power of 5. So in the same way, imaginary numbers also, when we are taking power, we are following the rules of exponents over here. So you are going to write this as I square to the power of 4 into I plus I square to the power of 9 into I. So which can be written as here minus 1 to the power of 4 into I plus minus 1 to the power of 9 into I. So because this is having an even power, you are going to get it as 1 into I plus, here you are having odd power, so minus 1 into I. So you are getting I minus of I, which is equal to 0. So now to write this as in the form of A plus IB, you can write it as, here you don't have both of the terms, so you can write it as 0 plus I iota, or 0 plus, or 0 plus 0 iota. Anything is the same. These both are the answers. Type of problem where we are having I to the power of minus 39. So how do we do this? We can write this as 1 by I to the power of 39. So which can be written as 1 by I to the power of 38 into I. So which is equal to 1 by I to the power of 38 can be written as I to the power of 2 whole to the power of 19 into I. This is equal to 1 by minus 1 to the power of 19 into I, which is equal to 1 by minus 1. Since it's odd power, you'll get it as minus 1 into I, which is equal to 1 by minus I. So we rationalize it with multiplying it with I and dividing it by I. You're going to get it as I by minus I square, which is equal to I by minus into minus 1, which is equal to I by plus 1. Therefore, here we are getting it as, therefore I to the power of minus 39 is equal to I is the answer, which can be written as 0 plus I, because it has to be written in the form of A plus IB, where A and B are rational numbers, and this is in the form A plus IB is in the form of a complex, it's a complex number. This problem, how to find out this solution, we'll see. It's given that 3 into 7 plus I7 iota 7 plus I into 7 plus iota 7. What is this equal to? So we multiply 3 inside, 3 sevens are 21 plus, here you are going to get it as 21 iota plus 7I plus 7I square. And we know that root of minus 1 is equal to I, and minus 1 is equal to iota square or I square. So here now you will get this as 21. All the like terms you can add over here. So 28I when you are adding these two, plus 7 into minus 1, because iota square is equal to minus 1. So now here 21 plus 28 minus of 7. So when you are minusing it over here, you are going to get it as 14 plus 28. I is the answer. Here you are having 1 minus I minus of minus 1 plus I6, which is equal to 1 minus I plus 1 minus I6, which is equal to, here you are going to get it as 2 minus 7I. Because I coefficient is 1, you will take it as 1, and therefore here you will write it as 2 minus 7I. The like terms you are going to add. Yeah, now what's the solution for the fifth one? We'll see. Fifth one, 1 minus I minus of minus 1 plus I6. So here what we'll do is, we'll first write down what is the problem. Here 1 minus I minus of minus 1 plus I6, taking the minus sign inside, we get it as 1 minus I plus 1 plus, this becomes plus into minus is minus 6I. So which is equal to, taking all the like terms together, get 1 plus 1 minus of I minus of 6I, which is equal to 2 minus 7I. So therefore we have 1 minus I minus of minus 1 plus I6 is equal to 2 minus 7I is the solution for this given problem. Next, going into the sixth one. So now what is the sixth one solution? We'll see here. It is 1 by 5 plus, problem is 1 by 5 plus I into 2 by 5 minus 4 plus, in brackets this is a minus of 4 plus I into 5 by 2, close the bracket. So now here how do we do this problem? We'll take again in the same way, we have to write all the like terms together, but before that we'll take minus sign inside the bracket, inside the second bracket. So what do we get? We'll see. Here it is equal to 1 by 5 plus I into 2 by 5 minus 4 minus I into 5 by 2. So now bringing all the like terms together, 1 by 5 minus 4 plus I into, you can take inside the bracket this, you can take out common, so 2 by 5 minus 5 by 2, which is equal to, here if you take LCM you're going to get it as 5, 1 minus of 20 plus I into, here the LCM will be 10, so 2 2s are 4 minus 25, so which is equal to, you're going to get this as minus 19 by 5 plus, here I into minus 21 by 10, so which is equal to, here you can write it as 1 by 5 plus I 2 by 5 minus 4 into, minus sign into 4 is inside the bracket, so you're getting minus of 4 plus I into 5 by 2 is equal to minus 19 by 5 minus 21 by 10 I. So we are all bringing this into the form of A plus IB. So this is the form which we write. Here next problem, the seventh one, is given as 1 by 3 plus I 7 by 3 plus 4 plus I into 1 by 3 minus, in brackets, minus 4 by 3 plus I. So how do we do this problem? We'll see the solution part. 1 by 3 plus I into 7 by 3 plus 4 plus I into 1 by 3, these two are in one bracket, minus of minus 4 by 3 plus I. So now first we'll open this first bracket and then take the minus sign for the second one. So here you'll get 1 by 3 plus I into 7 by 3 plus 4 plus I into 1 by 3, minus into minus gives you plus 4 by 3 minus I. So now bringing all the like terms together, you're going to get it as 1 by 3 plus 4 plus 4 by 3 plus, if I take out I common, here I am going to get it as 7 by 3 plus 1 by 3 minus 1. So which is equal to, you're going to get it as equal to 1 by 3 plus 4 by 3 is LCM, you can take it as 3. So 1 plus 4 3s are 12 plus 4 plus I into LCM is 3, means 7 plus 1 minus of 3, which is equal to 12 plus 4 16, 17 by 3 plus 7 plus 1 is 10 minus 3 is 7I. 7 plus 1 is 8 minus 3 is 5I. So you're going to get here 5I. I into 7 plus 1 minus 3 will give you, by 3 will give you here 5I. 8 minus 3 is 5I by 3. So therefore you can write this as 1 by 3 plus I into 7 by 3 plus 4 plus I into 1 by 3 minus of minus 4 by 3 plus I is equal to 17 by 3 plus 5I by 3. Now going into the next problem, that is the 8th one. What's given in the 8th one? You are having 1 minus of I whole to the power of 4, which can be written as 1 minus I whole square into 1 minus I whole square. So therefore this will give for us, you can write it in this way. You know what is a minus b whole square formula we can use for this, which is equal to a square minus 2ab plus b square. So therefore 1 minus I whole square is equal to 1 square minus 2 into 1 into I plus I square. So which is equal to, you are going to get it as 1 minus 2I plus I square, which is equal to, here I square is nothing but it is equal to minus 1. So 1 minus 2I minus of 1, this will get cancelled. So you are getting it as equal to minus 2I. So here we are having 1 minus I whole square is equal to minus 2I. So here 1 minus I whole square whole to the power of 4 is equal to 1 minus I whole square into 1 minus I whole square, which is equal to minus 2I into minus 2I, which is equal to 4I square, which is equal to minus 4, since I square is equal to minus 1. I square is nothing but I is nothing but iota. It's a complex number which can be written as a combination of real number and an imaginary number. That is called a complex number. So you are calling this imaginary number as iota. I square is equal to minus 1. So next, 9th one, we are having 1 by 3 plus 3I whole cubed. So we know that a plus b whole cube formula, we are having a formula for a plus b whole cube. What is that? We'll write down. It is equal to a cube plus 3a square b plus 3ab square plus b cubed. So which is equal to, you can write this as 1 by 3 plus 3I whole cubed is equal to 1 by 3 whole cube plus 3 into 1 by 3 whole square into 3I plus 3 into 1 by 3 into 3I whole square plus 3I whole cubed. So this is written as 1 by 3 plus 3I whole cubed is equal to 1 by 27 plus 3 into 1 by 3 into 1 by 3 into 3I. So this 3 and this 3 will get cancelled, plus 3 into 1 by 3 into 9 into I square plus 27I cubed. So this is equal to, you can write this as 1 by 27 plus, here you are left over with only I over here, because all are getting cancelled over there, so only I is left out over there, plus here 1 3 will get cancelled over here. So you are getting here 9I square plus 27I cubed. Now we know that I square is equal to minus 1. So this is equal to, you can write this as equal to 1 by 27 plus I plus 9 into minus 1 plus, this can be written as I square into I. So which is equal to 1 by 27 plus I minus 9 plus, here 27 into minus 1 into I. So you are going to get it as equal to 1 by 27 minus 9 minus 27I plus I. So therefore this is equal to, I forgot to write the I between, so I wrote it here. So therefore this is equal to, You can take the LCM. LCM is here 27. So what are we getting? 927 into 9 is 9 sevens are 63. 1 by 3 plus 3i whole cubed is equal to minus 242 by 27 minus 26i. Next, going to the next problem. Here we have, what is the next problem given? It is minus 2 minus 1 by 3i whole cubed. So again here also we can use the formula minus 2 minus 1 by 3i whole cubed. So a minus b whole cubed is equal to a cube minus 3a square b plus 3ab square minus b cubed. So here for us a is minus 2 and b is minus 3 by 3i 1 by 3i whole cube, which is equal to minus 2 whole cube minus 3 into minus 2 square into minus 3 by 3 into I plus 3 into a is minus 2 into b here is again minus 1 by 3 I whole square So now here how will we use this? We'll just see. Here you are having a is nothing but minus 2 and b is equal to 1 by 3 I. So substituting in this, what do we get? We'll see. So this is equal to minus 2 minus 1 by 3 I whole cubed is equal to minus 2 whole cube minus 3 into a square is minus 2 whole square into b is 1 by 3 I plus 3 into minus 2 into 1 by 3 I whole square minus 1 by 3 I whole cube. So we are going to get it as equal to minus 8 minus 3 4s are 12. Here 3 will get cancelled, so you can write here 4i plus here you are going to get it as 3 into minus 2 into 1 by 3 into 1 by 3 into I square. So here 1 3 will get cancelled and here minus 1 by 27 I cubed. So which is equal to minus 8 minus 4i. Here minus 2 by 3 I square minus 1 by 27 I square into I. So this will be equal to minus 8 minus 4i minus 2 by 3 into minus 1 minus 27 into minus 1 into I. So which is equal to minus 8. Here you are going to minus into minus is plus 2 by 3 minus 4i plus 1 by 27 I. So which is equal to, here you can take the LCM as 3. So minus 24 plus 2 minus, here you are going to get I, here you can take 27 common. So inside the brackets here you will be getting it as 27 into 4 is 4 sevens are 28. So 108 minus 1 into I. So this is equal to minus 22 by 3 minus 107 by 27 I. So therefore we can write minus 2 minus 2 minus 1 by 3 I whole cubed is equal to minus 22 by 3 minus 107 by 27 I. Next, going into the next one. Now the next set of problems are, you have to find out what is the multiplicative inverse of the following complex numbers. So the multiplicative inverse of the multiplicative inverse of 4 minus 3i is 1 by 4 minus 3i. Now we have to rationalize this 1 by 4 minus 3i. How do we do this? We'll see. By multiplying it with 4 plus 3i divided by 4 plus 3i. We have to remove the iota from the denominator. The imaginary number should not be there in the denominator. Like how we do for square root, the same way we have to do for this also. So this will be equal to 4 plus 3i by 4 square minus 3i whole square. So which is equal to 4 plus 3i divided by 16 minus 9i square. So which is equal to, we are going to get this as 4 plus 3i divided by 16 minus 19 into minus 1, which is equal to 4 plus 3i divided by 16 plus 19, which is equal to 4 plus 3i divided by 35. So this can be written as 4 by 35 plus 3i by 35. Therefore, the multiplicative inverse of inverse of 4 minus 3i is 4 by 35 plus 3i by 35. Next, going into the next one, root 5 plus 3i. So we have to find out what is the multiplicative inverse of this. The multiplicative inverse of root 5 plus 3i is 1 by root 5 plus 3i. Since you know that whatever is the inverse, if you are multiplying with the original value, it should be equal to 1. That will be the multiplicative inverse. So now here we have to rationalize this. So rationalizing 1 by root 5 plus 3i, we get root 5 minus 3i divided by root 5 minus 3i. So which is equal to, get it as root 5 minus 3i divided by root 5 whole square minus 3i whole square, which is equal to root 5 minus 3i divided by 5 minus 9i square, which is equal to root 5 minus 3i by 5 minus 9 into minus 1, which is equal to root 5 minus 3i divided by 5 plus 9, which is equal to root 5 minus 3i divided by 14. So therefore the multiplicative inverse of root 5 plus 3i is root 5 by 14 minus 3i by 14. Next, the 13th one, we have to find out the multiplicative inverse of minus I. So therefore the multiplicative inverse of minus I is 1 by I. So therefore here rationalizing 1 by I, rationalizing 1 by I, we have 1 by I into I by I, because we have to get rid of the denominator I. So you'll get I by I square so which is equal to I by minus 1, which is equal to minus I. So this is the multiplicative inverse of minus I is minus I itself. Okay, now going into the next, that to express the following expression in the form of A by a plus ib. So how do we do the solution? We'll see here. Solution for this. So first in the numerator we have 3 plus I root 5 divided by 3 minus I root 5 divided by root 3 plus root 2I minus root 3 minus I root 2. So we first have to here use the formula a plus b into a minus b will give you here equal to 3 square minus I root 5 whole square divided by here you are having root 3 plus root 2I minus root 3 plus I root 2. So you are getting this and this get cancelled. So you are getting in the numerator as 9 minus I square into 5 divided by here you are getting root 2I plus I root 2. Both are same. So you are getting 2 root 2I. So this is equal to the numerator part we are getting it as 1 minus of minus 1 into 5 divided by 2 root 2I because I square is equal to minus 1. So therefore this is equal to 9 plus 5 divided by 2 root 2I. Still more you are having in the denominator I term. So you are getting a 14 by 2 root 2I. So 2 sevens it is equal to 7 by root 2I. Again rationalizing this. So 7 by root 2I rationalizing. You are getting again you are multiplying it by root 2I by root 2I. So which is equal to 7 root 2I divided by 2I. I square I am sorry. So therefore this is equal to 7 root 2I divided by minus 2 because I square is equal to minus 1. So therefore the answer is minus 7 root 2 by 2I. This is the answer. Only for the we are having this as the answer for the whole problem. In the form of a plus ib you can write this as equal to, so you can write this whole thing 3 plus I root 5 into 3 minus I root 5 divided by root 3 plus root 2I minus root 3 minus I root 2. You are getting it is equal to 0 plus of minus 7 root 2 by 2I. This is the form of a plus ib.